Hello, everyone. My name is Dan Frumin, and I'm going to talk about our paper, Finite Sets and Homotopy Type Theory. Before I start, I would like to apologize for not being able to be there in person, and I would like to thank the organizers for giving me the opportunity to present remotely, nevertheless. So before the start, let us first say a couple of words about what we mean by finiteness. There are different intuitions for finiteness. For example, we can say that a set is finite if we can count the exact amount of elements in the set. Or we can say that a set is finite if we can bound the amount of elements in the set. Those notions are called Bishop finiteness and Kuratowski finiteness, respectively. Classically, those two notions are equivalent, but constructively there are some differences. There are several other notions of finiteness, but in this talk we are going to be concerned only with the first two. And the goal of this work is to perform a case study of Kuratowski finiteness in the setting of homotopy type theory. The material in this talk and in the paper has been fully formalized in Coq using the homotopy type theory library. So let us take a look at how to make Kuratowski finiteness precise in type theory in some sort of natural way. For the purpose of representing sets bounded from above, we can represent a set as a list of elements, possibly with some duplicates. However, we do hit some obstacles with this definition. Firstly, the propositional equality on this data type is not the notion of equality of sets. Instead, some sort of extensional notion of equality is desired. Under this approach, we make operations on sets from operations on lists. However, not all functions on lists are functions on sets. Specifically, the set functions have to respect this notion of extensional equality. In addition, this representation does not provide us with a useful proof principle directly. So the induction principle for lists is not directly applicable for proving properties about sets. For instance, the append function on lists is not commutative, unlike the union operations on sets. Now, there are several ways in which we can obtain a data type with the right notion of equality. The first approach would be to work in the category of setoids. And this is a very old approach, which can work in vanilla type theory. It doesn't require any extra machinery, but it can be quite cumbersome. Another approach is to work in type theory with quotient types. This requires an extension of type theory, and we need to perform some extra work for lifting the operations. And the last approach is to use higher inductive types in homotopy type theory. They give the right constructors and the right equations and proof principles immediately. All their approaches are valid and have their pros and cons, but in our work we're going to be concerned with the last approach. So we choose the later approach and work in homotopy type theory. From the point of view of homotopy type theory, if I can boil it down to some basic statements, we view types as topological spaces, we view terms as points in those spaces, and then we view the proofs of equalities as paths between the terms. The univalence axiom allows us to identify two types if we can construct an equivalence between them. Another bit is higher inductive types. In contrast to inductive types, where only point constructors are allowed, in higher inductive types we can provide path constructors as well. The exact syntax and semantics of higher inductive types is still up to some debate. However, the approach we take satisfies the general syntax for higher inductive types from those two papers published last year. In this setting, we define the higher inductive type of Kuratowski finite subsets of type A as follows. We have constructors for empty set, singleton, and union. That means that an empty set and singletons are considered to be Kuratowski finite, and if we take a union of two Kuratowski finite subsets, then the result is Kuratowski finite as well. In addition, we have path constructors that state that the union is commutative, associative, and satisfies the neutrality laws. Note that those constructors are inspired by a free join semi-lattice construction. However, one thing that is missing is an additional path constructor, trunk, that identifies all the paths. For instance, if we consider a set X union X, then there are two equalities between the set and itself. There is the identity equality and the commutativity one. The trunk constructor identifies them together. Before we see why we require this, we need to discuss how to define functions on finite sets by looking at the recursion principle. So recall the list-based definition from earlier on. One of the points considered there was the proof principle associated with the naive definition. Our high inductive type also comes with the proof principle that takes the equality into account. And in this slide, we're going to see the recursion principle in detail. If we had a regular inductive type and we would like to recurse into some type Y, then we have to provide the images for the point constructors. That is, we have to provide the image for the empty set in the type Y, all the singletons in the type Y, and the union operation also on this type Y. But since we're working with the higher inductive types, we also need to provide the images for the path constructors. That is, we need to show that the union operation Y is commutative, associative, and important and satisfy the neutrality laws as well. After we provide all this data, we can recurse from K of A into the type Y. This recursor satisfies the regular computational rule for points. There are also computational rules for the path constructors, but we're not going to be concerned with them in this talk, so I will not discuss them. We can also define an induction principle in a similar way, but it will be too cumbersome to state it, so we don't give it in detail. But you can imagine that it looks somewhat similar. Now we can motivate the truncation constructor that we had. So suppose we want to prove the following lemma. We want to show that the union operation is idempotent on the type K of A. So given any finite set X, we want to show that X union X is equal to X. We do so by the recursion on X. For the empty set, we need to provide the proof that empty set union empty set is equal to the empty set. We take the NR constructor, stating that the union is neutral with regard to the empty set. For the union constructor, this is an induction step, and we need to prove the following equation from the assumptions that x1 union x1 is x1 and a similar assumption for x2. We do so by giving a composite path P that contains some associativity paths, commutativity paths, and some other operations. So those are the images for the point constructors. But what about the path constructors? For instance, we have the NL path constructor in our higher inductive type. And for the image of this, we need to provide a higher equality between two terms that involves constructors like NL, NR, and this compound path P. In general, there is no reason for those terms to be equal. However, we're lucky in that we have the truncation constructors, which allows us to identify all the higher paths. So I hope this clears up this truncation constructor a little bit. Now that we've seen the data type in detail, we have enough to define functions on finite sets. As an example, let us consider the membership predicate. Before we dive into that, we have to recall the notion of propositional truncation. In homotopy type theory, it says that a type A is a proposition if it has at most one element, and we denote the universe of such proof-relevant types as H-prop. There is a propositional truncation construction which, given a type, constructs a proposition. The truth value of this proposition signifies the inhabitants of the original type. So intuitively, you can say that the type truncation A is the same thing as the type A with all the elements identified. Using this propositional truncation, we can define the membership predicate as a proposition. So given an element A of type A and given a finite set X over A, we provide a proposition A belongs to X. We do so by the recursion on X. For the empty case, we know that nothing belongs to the empty set, so A belongs to the empty set is false. A belongs to the singleton B if A is equal to B, And in order to turn this into a proposition, we truncate the identity type A equals B. For the union case, we know that A belongs to x1 union x2 to the extent that A belongs to x1 or A belongs to x2. And again, here we do this by forming a sum type and truncating it into a proposition. So those are the images for the point constructors. But what about the path constructors? Providing the images to the path constructors amounts to showing two facts. First of all, we need to show that hprop with the false proposition and union is a joint semi-lattice. And we need to show that all the paths between propositions are equal. The later statement is just a fact of homotopy type theory. And the former statement is proved by showing some laws. And showing those laws actually requires univalence. So for instance, in order to show that the image of the union operation is commutative, we need to prove this equality right here. And the way to do this is to actually construct an equivalence between those two types and then use the univalence axiom to get an equality. So this is the membership predicate. And besides having the right operations, finite sets also need to satisfy the right notion of equality. And the equality here is actually coincides with an extensional notion of equality. That is, given two finite sets x and y, we can show that x equals to y, given that x is extensionally equal to y. That is, all the elements for all the elements A of type A belongs to x if and only if A belongs to y. To prove this, we go through a chain of equivalences. We first show that the type x equals y is equivalent to the type x being a subset of y and y being a subset of x, but written in a more algebraic way using union. And then in turn we show that this type is an equivalent to our desired statement, and we do so by nested induction on y and x. A similar method can be used to show that the equality on K of A is decidable whenever A itself has decidable equality. Now we can take a look at an application of this data type, namely defining the actual notion of finiteness. And the idea here is that we think of each finite set X with elements from type A as a certain subobject of A. Then K of A is a subcollection of subobjects of A, specifically the collection of Kuratowski finite subobjects of A. Then we can use the standard category theoretic definition of Kuratowski finiteness, that is, a type is Kuratowski finite if the maximal subobject of this type is finite, to arrive at the following definition. We say that a type A is Kuratowski finite if there is a finite set X such that every element of A belongs to this set. An alternative definition that we also mentioned earlier is Bishop finiteness. This notion has been studied before in the setting of homotopy type theory and has been formalized in the Unimath library and the homotopy type theory library. According to this definition, a type A is Bishop finite if there is a natural number n such that A is merely equivalent to a canonical cardinal of size n. Note that all such finite cardinals have decidable equality. We can then show that every Bishop finite type has decidable equality as well. This lies in contrast with Kuratowski finite types, which need not to have decidable equality in general. And this begs the question, how we can compare those two notions? Well, firstly, by induction on the size of a set, we can show that every Bishop finite type is Kuratowski finite. However, the other direction does not hold in general. For example, we can show that a circle S1 is Kuratowski finite. But assuming univalence, we know from the work of Licata and Schumann that circle doesn't have decidable equality, hence it cannot be Bishop finite. To better compare those two notions, we need to generalize this from finite types to finite subobjects. We already know what Kuratowski finite subobjects are. They are sets from the type Ka. We say that a subobject P is Bishop finite if the corresponding subset is Bishop finite as a type. We can summarize the comparison in the following table. In this table, we use the notion of decidable mirror equality. This notion is similar to decidable equality, where I use the truncated identity type instead of the usual identity type. So, for instance, we can show that all the singletons are Kuratowski finite, because the singleton is a constructor for the data type K of A. For bishop finite subobjects to be closed under singletons, it is required that the underlying type is an H set. That is, the type A shouldn't have any higher path. For an H set A, if we want bishop finite subobjects to be closed under union, we need to have decidable equality. But for Kuratowski finite subobjects, this operation is always definable, as it is a constructor. For the intersection, the requirement of bishop finite subobjects is the same as the requirement for the union operation. But for Kuratowski finite subobjects, we can say that the intersection is definable if and only if the underlying type has decidable mirror equality. And we can show similar result for the decidable membership predicate as well. So we can then show that under some conditions, those definitions coincide. Specifically, if the underlying type A has decidable equality, then the Kuratowski finiteness of A implies the bishop finiteness of A. This is shown by the induction on the finite set witnessing the Kuratowski finiteness of A. Here we need the condition of decidable equality on A for the union case. As we've seen from the table on the previous slide, if A has decidable equality, then bishop finite subsets are closed under union. And this is the crucial part in this proof. Another application that I'm going to briefly mention here is the interface for finite sets. And the idea here is that for writing programs, some concrete data structures like binary trees or lists are more efficient and better in practice. Then Ka is more of an abstract version of finite sets, which is more suitable for reasoning. So we're going to transfer operations and properties of those operations on Kuratowski finite sets to those on concrete data types. To make this precise, let us first define an interpretation of finite sets. We say that the type T is an interpretation of finite sets over A if it satisfies a certain signature. Specifically, the T should contain an empty set, there should be a union operation on T, and for each A in the type A, we need a term singleton A belonging to the T. In addition, for each A in the type A, we require a predicate A belongs to, which signifies the membership predicate. Then a homomorphism between two interpretations is just a function that commutes with all the operations here. Note that the signature here is not algebraic because of this family of predicates that we require. Then an implementation of finite sets is a type family T such that each TA is an interpretation of finite sets, and for each A we have a homomorphism from T of A to K of A, where K of A is an interpretation of finite sets in a trivial way. Such homomorphisms are always surjective. It can then be shown that the functions on K of A can be carried over to any implementation on finite sets just by precomposing with this homomorphism, and some properties of these functions carry over. Let us illustrate this by an example. An example implementation would be lists. For each A, we have the type lists over A, and it implements finite sets with the empty list as the empty set, with the append function representing the union operation, and the membership predicate on lists representing the family of the membership predicates. Then the homomorphism from list of A to K of A is just a folding operation, which collects all the elements in the list. So with this, we can lift operations from K of A to any implementation while preserving properties. So for instance, we can define a universal quantification on finite sets. Given a predicate P and a set X over A, we can construct a proposition for all Px, which signifies that all the elements of X satisfies P. And this proposition comes with the following property. If we have an element A which belongs to the set X, and we know that P holds for all the element of X, then we know, for instance, that element A satisfies the predicate P as well. This operation can then be lifted to lists just by precomposing with the homomorphism. And this operation will in turn satisfy a similar property. If we have a list L and a term A, which is a member of the list L, and we know that P is satisfied for all the elements of this list, then in particular we know that element A satisfies the predicate P. The proof of this is simple, just by appealing to the definition of the universal quantifications and the property of the homomorphism. Similarly, if the type A has decidable equality, we can define several other operations on the Krotowski finite sets over A. For instance, we can define the cardinality function on the finite sets, which is then being lifted to the cardinality functions on lists. And this operation satisfies certain properties with regard to other operations on finite sets that are in turn transferred to the cardinality functions on lists. And in addition to that, we can have a decidable membership predicate on K of A, again if A has decidable equality, and then this operation can be lifted in the same way to the decidable membership predicate on lists. Okay. In summary, we've seen a formalized development of finite sets using higher inductive types. We've seen a small comparative study of Bishop finiteness and Krotowski finiteness in homotopy type theory, and we've seen a simple interface for finite sets which is suitable for data refinement. The source code for all the theorems and propositions in this presentation, the paper, can be found either on the CPP website or in the link shown here. Thank you for listening.